Hi, everyone. Welcome to another episode of the Haskell Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. Today, we're going to be continuing our discussion on functors. This is material that is referencing in the book chapter 16, specifically section 16.7 through 16.9. If you are following along in Haskell Programming from First Principles by Julie Maranuki and uh, Christopher Allen. Last time, and it's been, I know, a few weeks since we last covered this, we talked about what is a functor and some basic laws in order to actually build a functor. And it's hard. Haskell provides the functor type class using, um, uh, as I said, the kind of mechanism that's built for all other type classes. And that is, it defines as operations for something to be a functor. Um, But in addition to that, the design pattern itself of a functor requires you to actually build for your specific type class instance a certain set of laws into the implementation of the operations, um, specifically the laws of identity, composition, and structure preservation. These, unfortunately, are characteristics of the type class instance that cannot be enforced by the type checker. At least at this time, GHC's type checker, which is the more dominant Haskell implementation most folks use, does not provide a way for you to actually go in and check at compile time that certain laws for a type class instance are preserved so that you can actually um, leverage it. You'll end up almost always getting cases where you may have thought that you've implemented a valid functor and it turns out to be invalid. So doing your due diligence and making sure that you adhere to those laws is important. And today we'll be discussing some ways of actually enforcing that at the very least through the use of testing and testing frameworks such as Quick Check that we've talked about a few episodes ago.
Yes.
But before that, I wanted to at least talk about a little bit on the kind of notion of functors again. Not so much focusing on functors laws like we did last time. Although, as you can see, we have some examples here that kind of reference where the discussion left off of functors that could be valid or invalid, like in this case with the functor foo going in one direction where you did not provide proper identity preservation and in the second example that is commented here. Um, Let me actually do something here. Let me change the color scheme here just to get this a little bit more decent. Let's see if dark blue. Oh, it's already a dark blue. Let me try evening. Uh, Color scheme, evening. Um, that's still kind of, let's just do the default color scheme. No, that doesn't work either. Hmm, well, we'll stick with dark blue now. If folks have trouble reading this code as I go through, I will be more than happy to post this on Atlanta FP's GitHub repository for you to follow along. Although some of these examples are referenced in the book, so I encourage you all to just type them out from the book if you guys are following along with the book. So one thing I noticed when we were going through 16.7 through 16.9 is, at least when I was covering it myself, that I thought would be a good point of discussion today is to talk about this constant repetition of what they're of lifting inside the book, and they constantly bring up this concept of when you have a type, you are essentially lifting the type into the functor when you are building it, and I didn't quite get what this lifting concept was until I did some exercises. And at the suggestion of what the book provided, it was really typing out the type classes and working through how the evaluation worked really kind of drove home what this notion of lifting is all about. So I thought I would at least discuss today. We'll be talking about what is lifting, what is this notion, what exactly is the functor type class instance. Well, more importantly, how is the functor type class mechanism applied? Is the functor type class mechanism applied when you are dealing with particularly f mapping over a particular function over a collection of some sort? Because this is where lifting becomes very important, and the notion of what it is all about becomes very important. Uh, to begin with, I thought I would just do one thing here. I already have this open, and let me do this. Let me quit out of this and reload my GHC for today. And let's go ahead and load Functor Overview. Okay, that's good. And let me do one more thing here. Okay. Zero. Well, okay. So let me just pull this down and pull this up here. Okay. And all right. So I thought we would start with a simple example that the book kind of went through, but honestly, it didn't go into as much detail, and I actually am appreciative of that. And I thought we would be able to go through here to explain the notion of lifting. All right. So to begin with, we need to set up a couple of things. All right. One is we need to set up kind of a simple uh, function that we're going to use for our lifting example. All right. Um, this function is going to be using the const function, and for folks who don't remember what the const function is, the const function is already built in the Prelude, and it's a two argument function that allows you to um, take in an A and a B and it will return the first value always. All right, so you could create different functions of different constants, like say 5 equals 5, and anytime you call 5, it will, sorry, if you call 5A, 6 or something like that, it will always return 5. Okay, so f of x is 5 is what the constant function is creating. It's just a constant a function that will allow you to create constant functions. So with this constant function, we can go and define, let's say, a function called, let's say, replace with p. This is kind of what something the book does, and this function is nothing more than a function that takes in an a, returns another a. Right? So let's go ahead and load this here, make sure that everything kind of works. Would you type it? Hold on one second. Did I mess this up? I may have messed this up again. Um, I have to do this and it'll return a constant. Here we go. So now this function, now if you call this with any value, it will always return a uh, a character p. All right. So far so good. What we're going to do is we're going to go and we're going to create essentially um, three values. Okay. We're going to start with just um, a in the simplest case, a type like say either. Either is sorry, not either, a maybe, which is has a either nothing or just. And we're going to go ahead and create an instance of a maybe type by taking in and defining a maybe type here. And of course, since we're typing this in our text editor, we need to obviously provide um, that we are creating a maybe list of characters. Let's go ahead and load that, and we see that it's getting loaded. And we'll see that if you actually call directly the function on this maybe type, okay, that you'll get the value p, right? What the notion of functors does is it will, using again the pattern mechanism that's available inside Haskell, is it'll look up to see if there's a functor type class instance available for the maybe type, which there is. And if you call fmap with place with p, all right, what it's now doing is it's not it's going to go ahead and go into that functor instance for maybe, and it uses its implementation to essentially unwrap the outer piece, which is the maybe type, to access the inner value, which is in this case our string, and it will go ahead and um, apply replace with p to that string. All right. So first questions to most people is um, does this kind of make sense? So when we go and run fmap, we saw replace with p on avenue providing us with p, and that makes sense because it's a constant function that takes in anything. It doesn't unwrap or do any sort of magic, and it will go and return it. But what surprised me on this first example is when you apply fmap to replace with p on avenue, you end up getting just p. Now, to the new Haskell folks who read this in the book or have seen this, this might be surprising to you as well. And but it makes sense if you think about what exactly fmap is doing. All right, and what the notion, the functor mechanism does. All right, and this is ultimately what lifting is all about. Okay, so lifting is nothing more than taking the functorial structure, verifying that literally there's a type class instance that we can apply a function on. So that means there's an implementation that we can use of fmap, and applying that to the underlying value um, that is wrapped around this functor type. Okay, so in the case of maybe, you are unwrapping the maybe to get the value that it's holding, and you're applying the function to that value. But, and here's the kicker, you're applying that value as is. Okay, so what that means is if there are types inside this higher type, okay, this kind, all right, in case in the maybe type class, sorry, in the maybe type, and if that itself, if the value itself is has functorial structure, the functor will not actually recursively apply itself into that value. It doesn't keep on going until it hits some sort of primitive type where there's no more functor type classes available to apply on. All right, this is a little surprising to most folks, but this is why in the case of, if we look at again what avenue is, it's a maybe of character list of characters. Okay, maybe has a functor type class instance. You could look at this by just simply typing in info on functor, and you'll see that um, it's available. There's a already default implementation for the list functor and the maybe functor. But what that means is if you have an outer type um, that has a functor structure, and you call fmap with a function on that outer type, it will look up that type class instance if it's available, and if it is, it will apply it. But it only does it once. In order for you to constantly, which means that for any nested structure where there may be one or more functor um, structures that you want to apply a particular function into, or you're trying to traverse through until you get to the underlying most innermost value that to apply the function on. For each functor type or higher kind of type, you have to go and call fmap on, and this is where composition comes into play. All right. So what that means is if we want to actually apply um, fmap onto the underlying representation of avenue, which again, for folks who don't remember, avenue is actually just with a string of avenues, we need to actually compose um, uh, the fmap with another fmap before calling replace with p. So what that would look like is something like this. We do fmap.fmap, replace with p, and then we call avenue, and you could see that it will just apply the actual thing. So the first fmap, the outermost fmap is going to be applying on the maybe functor, and then what we're doing is we're looking up the list functor in the innermost fmap, and that's ultimately is what's taking in the replace with p function and applying it to uh, each of the individual values. All right. So that's why you end up getting PPP, because remember, the implementation of just is um, nothing more than look at if you go and look up the implementation for the instance on the maybe for nothing, it's in, if we do fmap nothing f nothing, you get nothing, and then if you look at fmap f just a, you'll end up getting just f of a. Okay, so that's what the first fmap does. And then, of course, for the other one, you have two cases for the list functor where you have the empty list, and then you have the cons list rule. I encourage you to go look up on Google the actual definition, so you can get an understanding of the rules that are associated with that. We're going to go through a couple of other examples here, but this is actually a very important thing to realize because it has a direct effect on how you write your type signatures for your functions that are taking particularly nested structures that where one or more uh, functor applications, fmap applications must be used in order to have an operation correctly get evaluated. I'm going to pause here to see if there are any questions. And in the meantime, I have to do one thing here. Okay. And okay. For folks who are watching our live stream, I do apologize ahead of time. I am trying to prevent some of this spam that's occurring on our stream in the live chat. But if you have any questions, feel free to uh, ask questions.
Hey, so this is nothing but map function, right, in Scala. So I'm basically a Scala guy. So it is basically applying map function in list probably.
This is actually a generalization of the map function. So there is a map function in Haskell, all right, that can be applied on a list. So in Haskell, you can do something like this. Simply, this is using an anonymous function. Um, and apply it, and it will work the way you expect it to. But if you want to generalize it to this a more collective structure, you need to provide certain rules, and that's where functors come in, and that's where fmap is specifically comes into play, because it allows you to then for anything that may not be a list, if there is a way to define an identity for that particular type of object, and some way of composing, doing function composition for some objects where you're returning other objects. You can actually apply the functor type class. You could define actually an instance of the functor type class for your type and define fmap on it, and it'll then just be a simple fmap on with an anonymous function on that object instance.
So, Rom, can we apply just plain map, not fmap, to a tree? Right. So
No, not as far as I know.
that's good. That's fine. That's what fmap is for then. Okay.
Yeah, I don't believe you can apply fmap a map on no normal map will not work at
Okay.
all. And if you
Great.
look at the type class on map, it restricts. Sorry, the type signature on map. It specifically restricts itself to only lists.
Okay. Good.
All right.
So yeah. So then fmap is the general function across anything that is I don't know. Uh, traceable, basically. Right.
Right.
Okay.
If you can define something that is traceable, you can more than likely define and something that has structure, a particular type of structure. You can certainly define a functor type class on that structure preserving object.
Yeah. And as always, it's up to you. Right.
Yeah, it's up to you. Has one famous person on YouTube that Judd and I are very fond of, Mr. Brian Beckman, once said, "At the end of the day, the how you implement those laws, identity, compositionality, and structure preservation is entirely up to you. But you just need to make sure that those are preserved in order for it to be considered a valid functor." And
Cool.
this you will hear us you will hear me beat this down, especially as we go on to talking about applicatives and monads and even monoids and other type classes where that are available in Haskell, where certain properties must be preserved in order for it to be this particular type. And unfortunately, and since we have someone coming from another language that implements these features, I'm always curious. As far as I know, GHC does not provide any sort of compile time type checking to make sure these laws are preserved. I don't believe Scala does that, but I'm unfortunately not a Scala expert. So I will
Yeah,
defer
it
to.
doesn't.
Could you say that again?
It doesn't actually.
Okay, it doesn't.
Yeah.
Okay, that's what I figured. Okay, thank you. So it's really hard. Don't get me wrong. I would be very surprised if they would be able to do some of this stuff. But again, as we will see later on, you can at least work around this by adding tests and make sure those tests are preserved. And if you do that correctly, then you'd be okay. All right. So let's go on and talk through a more complicated version. So we saw that here, you know, one application of a higher level, type, specifically the list functor with a maybe functor on it, and how we deal with it by just lifting first. Again, when we talk about lifting, we are literally removing a layer, but as far as the application is concerned, you're really constructing a new instance of this outer shell, and each shell, like I'm forgetting what those dolls are, those Russian dolls. Each fmap is removing one one layer of the Russian doll until you get to the ultimate value that you're going to apply the function on. And we've just seen this with
Matrushka.
Machushka.
Matrushka.
Matrushka. All right, a Matrushka doll. Yeah, it's the same idea in terms of functors, and I think it's actually a good analogy if that helps as you go through it. But let's go through one more example of this. So we saw already that if we apply fmap alone, it will just apply it to the value as is. We saw that, but it will more importantly, sorry, if we apply fmap first, it will only deal with the outermost type, and it will leave the underlying value alone. And each fmap compose will remove one more outermost type to go through and apply the function to that value. And each level that you do this, you will end up seeing more applications. Um, to make things a little bit more complicated, let's go ahead and create another couple of values. Okay, and it's going to be nothing. Let's go ahead and then also make a W, maybe character, and let's say W is just. These are all these examples are all referenced from chapter 16. I'm only showing this because I think it's important in us to at least discuss this example. And let's talk through also, let's create a list of these characters. And let's go ahead and create V and W, all right? So we now have, if we load our, I could just do reload, I think. And if we look at it, we end up just having our values here. If we just call, again, replace with P on LMS, we see that we'll still get P. Again, this is because replace for P's application has no idea what the underlying structure is. It knows that it's just some sort of valid type. It'll go through and apply it, and since it's a constant function, it'll return just P. All right. If we call fmap alone, okay, just the first time on this, okay, what is the type signature of this particular thing? I think it's important for us to recognize this and do it layer by layer. All right. I'm going to just show you the output of this. It might be surprising to some of you, may not be surprising to some of you, but when you apply this as LMS, you'll end up getting this, right? So what is the actual uh, type signature of this fmap application? We can actually go ahead and query this, obviously, if we just do :t, if I remember correctly, and just apply LMS to this. You'll see that the underlying functor is just returning a string of characters, as you just saw earlier, right? But why is it a string of characters? Well, it goes back to what fmap is doing, right? Fmap is getting a list. Okay, remember, fmap is getting what replace with P, just avenue, nothing, and just woohoo, right? So the only thing it knows about is the outermost list. Okay, and even though it is getting a list of maybe strings, right? So the only thing you can do is go look up the list functor for this and apply it, right, to each one of these values. So what you ultimately get is nothing more than what we saw before. We'll see replace with P, my apologies there. You'll end up getting essentially a list with replace with P, calling just avenue, replace with P, calling nothing, and replace with P, calling just woohoo. Now these are treated like what we saw earlier when we called replace with P on the actual top level list, which means these are all constant functions. So when you actually go and evaluate this, each one of those are just going to be a single character p. All right. And then since uh, there's a type alias inside Haskell that treats lists of characters as strings, it's going to automatically invoke the show function, the show instance for that string, and that's why you end up getting a string of 3Ps there ultimately on the command line. This is how all of this works. All right. So what we've ultimately done is in this level is we first, we lifted just the values of the maybe types into our list, and we're applying the function to them. Okay. But what if we want to actually go one more level, right? What if we want to actually go and actually apply replace with p on the each of the individual strings? Well, the first thing you may be thinking is then we might create something like, say, fmap, just so for convenience sake, I'm just going to go and create this function here. We might end up calling fmap twice on replace with p, and apply it uh, with LMS, right? Thinking, oh, this is going to allow us to apply that function to the underlying list of strings that are available to each of those instances. But as we saw before, again, this is only going to unwrap the layer twice. So it's going to first apply the list functor, and then it will apply the maybe functor. So what you ultimately are going to get is actually this, right? Which is um, again, not actually dealing with the fact that each string is a list of characters and applying a list functor. It's not doing it recursively again, like I said. So it's just calling replace with p on that value and treating it like some sort of constant type variable. All right. So the way to fix this is obviously when you are dealing with is to call essentially fmap, compose fmap 3 times, right? Saying that, okay, we know we're dealing with the list, we know we're dealing with a maybe, and we're ultimately going to be dealing with another list. Let's go ahead and do that. All right, we've you know we gone through all the layers of the onion, and we've actually found the underlying value that we're ultimately going to apply on. And we're going to do this for each of the individual characters, because remember, it's a list of characters. And then what we ultimately get is what we'd ultimately expect, which is um, just PPP, nothing, and just with 6 Ps. All right. The bottom line here, and it took me some getting used to in writing this out, and I encourage you, as you are doing this, at these exercises, and you're working through this book, and you're working through functors, to go through the exercise and figuring out what the type signatures are, just because you may be surprised based on what it's doing. And it certainly surprised me, because I thought it was one thing versus another. And it really required me to go through the exercise of writing it on paper and clearing things up to recognize what is ultimately happening. This is regardless of whether or not you're using functors in any language. If you're dealing with functors, you are dealing with this kind of mechanism of a multi-layer cake that you need to go and unwrap in order for you to get to the actual values that you want to apply your functions to. All right. So hold on, let me just see what time it is. Okay, it's 2:46. Um, the stacking of fmaps are actually quite natural. All right. And it is something that becomes extremely important, and you could do specializations by and provide certain specializations uh, if you are so inclined. Uh, to illustrate this, there was this nice example in the book related to essentially type signatures that you might apply in a program that I'm just going to kind of show you here. Um, That's our next example here. So you can start with what we had before, which is our constant value, a constant function. And obviously, this is our data that we set up for our example. Um, but you might want to, take this constant function here and, change what is ultimately going to be and change its signature. So like in this case here, replace with p prime is taking in a list of maybe characters and then passing in returning a character. And all it's doing is this aliasing itself to replace with p. All right. You can do this in Haskell and change it, provide a new function with a different signature that's much more stringent than the signature that you originally provided, and it's okay. This new instance will treat that; it'll be more stringently type check. Same idea can be applied to if you're dealing with functors. All right. Here we have a generalization of applying a functor once, twice, and 3 times. All right. And as you can see in each one of these, the order actually of the function application matters, all right? The functor application matters. So in this first one here, we're just apply since there's only one functor that we're applying to, we're just calling fmap with replace with p, making this, each of these are specializations on fmap with replace with p using composition. And the reason for that is that obviously once you get this specialization, you have the nice convenient name for that specialization. You can actually just use it directly and makes your code a little bit cleaner. This is just a standard practice to follow. But the important thing to realize is if you're passing in a value into this function or applying this function to a value that has some sort of functorial structure, it's going to go and do the simple lookup for the outermost functor that needs to be applied, and then we'll go and apply that fmap implementation with this function, the function that was passed in as the first argument. In this case, it's replaced with p. You can also take this and be more stringent like we did earlier. We can actually say, well, we are expecting always a list of maybe strings. So let's go ahead and do that. Let's create a function that takes in a list of maybe strings and then returns a list of a list of characters, or in this case, a string, and let the type checker do the nice, input validation for us at compile time. And hold on one second. There looks like there was a question here. One second. So there was a question here earlier that I just noticed. Uh, is the question on how does fmap know what to do to find the value been answered, or is there any or do I need to elaborate on that? I think Judd, you actually asked this question.
Yeah. So I mean, actually, your explanation is good, and so basically, if fmap is taking some value, then it's going to go grab that value, which is pretty much just a pointer, right? But then somewhere it knows that okay, this pointer points to some structure that's defined and recorded, right? Like a list or a maybe or something like that, right? And then so fmap is literally, I mean, as you pointed out, fmap is literally unwrapping one layer. If you define it correctly, right, it'll try to do it. And if you've gotten all your ducks in a row, it'll work. But it's literally only taking some complex structure and saying, okay, take the outermost structure off of that and let's operate on the things inside that.
Yes, that's exactly right. That's a good way of putting it. Yes.
Okay, cool.
So um, this ability to actually quickly do the making these stringent checks can be best be seen here. And when you're creating your APIs, some folks will start off with a generalized you know set of utilities that look like this with the ultimate type check. And that is the ultimate functor checks are done ahead of time, has part of the function signature. But once you have this in place and you're creating this alias, having these more stringent type checks, especially has a public API, is very, very useful. So I would encourage more folks to kind of follow this pattern of creating this as a utility function and ultimately applying it and creating aliases to it for other functions for different types, especially more frequently used types, because that would certainly help users when they see some of the error messages that are coming in from the Haskell type checker. Um, we could see this quickly being used here. I just briefly implemented some of this. You could see that if we could go ahead and put, stir into, let's go ahead and do twice lifted here and thrice lifted, twice lifted, and let's go ahead and that. And if we go ahead and run this, let's go ahead and quit this out here for a second or load now. The example, we could see if we go ahead and run main here that this is what it kind of looks like. I'm going to go ahead and clear up this so you can actually see this. So the first time we run replace with P, remember replace with P prime is just taking in our list of maybe strings and returning in characters. We could see that what we're going to get the first time is nothing more than a constant value. But when we lift the value and take the outermost shell of the list, right, we're actually applying it to each value like we did before, and that's going to create our string, right? And this doesn't matter if we apply the functorial structure using the general type signature or the more restricted one that we saw has indicated by replace and replace prime. The second and third one, although we do have implementations of doing the more stringent version or not stringent version, it's just calling the functorial structure just to reiterate the point that I was saying earlier, which is when you're dealing with function compositions, each fmap is just going to unshed one more layer there. And trying this and playing around with this, I think it becomes very useful for folks to go through and understand. One thing that I found very odd when I was going through this was the next topic, which is talking about bef- the next topic is a confusing topic for me, but I think it's a topic that I kind of understand now. But to illustrate it, I'm going to have to come show and ask a question, right? And that is, what do folks think output is if we do? Again, remember, we have a bunch of type classes instance here, all right, for various types here. What would you think be the type or the return value if we call replace with P on, say, here, right? If you think replace with P here with fmap is going to apply that function replace with P on 10 and 20, you would actually be very surprised. All right. And the same thing actually happens if you use if I remember correctly, the either type. So let's say that we create an instance X on, say, I think either 10 or 20. All right. Wait, I have to create, I don't get that pair anymore. Give me a second here. What do I have to do? I have to do left 20 or right 20. So let's just say x equals left, right? And uh, um, right. So these are both either types here. Make sure that we have either A or B. If we apply Fmap on, say, replace with P, on Y, we would end up getting what we would expect, right? But if we call replace with P on X, you'll see that it will not actually apply the function replace with P on X. And the reason for this is the same reason for pairs. And we're going to get into that in a minute. But if this is surprising to most people, it's because of a very simple case. And it goes back to what the kind is for pairs and either types. All right. So let's look at the kind of uh, pair, for instance. Okay. Pair and either, all right, are both higher kinded types. If you remember our discussion on higher kinded types, a kind is a and and it's information to tell the type checker whether or not something has been realized, a type has been realized or not, whether or not something is a parameterized type that needs to get all of its type variables bound before it actually becomes a valid concrete instance for the use of type checking. All right. Pair and either being higher kind of types means they need multiple types in order to become fully realized. And remember, a fully realized type in Haskell is indicated by just a star. All right. So that was star, arrow, star, arrow, stars. Think of them as functions. Those are multi-argument functions where each star represents a concrete type that needs to be passed in. Okay. Functor and all the type classes for that matter, all right, do not deal with higher kind of types well. They expect that you are dealing with um, a, a kind of just star, arrow, star, all right? That a higher kind of type is a multi-argument application of that function. A star, arrow, star means that you have a parameterized version of it, okay? So that's okay. Okay, and we've seen that with list. List is, if you look at the list of kind is a star arrow star. All right, it's a function that takes in a type variable and returns a concrete type variable. All right. So if we were to create a functor type class instance for these, we will get into trouble. And the best way to explain this and illustrate this is actually come up with another example here. Let me go back to our overview here. Go here. Let's go ahead and create, just a simple um, class called, say, let's just call it, pair. I don't think pair exists right now. So we could just go ahead and say pair um, AB deriving EQ and show, just so that we can actually get to some very nice things from the command line. And let's go ahead and uh, create the same kind of idea for either, just so that we could check out the either problem too as well. Um, but let's do that after we come up with this implementation for pair. So let's go ahead and reload load functor. Okay. And so as you can see, we could do pair 1020 and we're okay. So let's say that we want to define a functor on this, all right? So if we just simply create an instance, functor on 2, and we don't define, let's say, anything for the time being. And we try to load this, you'll see immediately that you're going to get an error, right? Oh, sorry. Um, thinking what's in the book, and I was actually typing in the wrong thing. The thing about this error here is it tells you a lot if you can understand what it's saying. Pair expects one or more type variables. All right. The functor type class and all type classes expects a kind. All right. Of star arrow star, meaning that it's expecting a parameterized type of one type variable. That's it. Pair, on the other hand, is expecting that you provide um, some sort of is a higher order, higher kind of type, right? So it's expecting two type variables, right? So it's going to actually go and say that, oh, well, the reason why we can't create an instance of this is because um, this is not star arrow star, right? So you might think that, oh, well, that's pretty easy. We could just go ahead and maybe do something like um, create a specialization where we don't necessarily need to know what type variable we have, but we have, something like this. And then we could just simply then say f of pair AB is, we're going to call pair on the value of f of A and f of B. That seems okay, right? You think that, oh well, this should work. We're specializing on the type. We created we created now a single kind of type. Everything should be fine for the compiler. We should actually be able to apply now this function to the both the values. And as it turns out, that's also wrong because the functorial signature, all right, the functor signature of the type instance has now fixed A. It has fixed a type variable A, all right? And therefore, because it is part of the functorial structure, now because it has fixed itself when you put it as part of the type class instance, we are not expected to touch it. We cannot touch any instance of it. The values of it are fixed. By putting it in this signature, you have ultimately told the type checker and the Haskell compiler that this value cannot be modified. We're not supposed to touch it at all. Okay. And therefore, what's it's going to end up happening is it's going to complain about um, the fact that we're trying to apply a function to a fixed argument. The same problem actually occurs um, uh, when we're trying to deal with the either type, which is whether left or right. And that's because, again, once it's part of the signature, it is going to complain. All right, it is going to complain. Um, to see this even with that, let's go ahead and first fix this here because this will not work. We've got to do this and we actually now work. We have a proper fmap on it. So if we do fmap of replace with p on a pair 20, you can see that we get pair 10 p. And it's the same with if you end up doing with either. So for folks who want to actually be able to apply a functor in pairs on pairs like that, where it's applying it to every value. As far as I can tell, such a mechanism does not exist inside Haskell. Um, I don't outside of you know creating the pair as a list and then using the list functor, but that's kind of neither here nor there. You're actually losing function type safety by doing some of that kind of crazy stuff where you're dealing with some of the structures. You have to be a bit more careful with that.
Yeah, I think that this actually makes sense
Hmm.
because um, a tuple can, unlike a list in Haskell, so a list in Haskell must be uh, homogeneous, right? It
Right,
has to
that's
be,
right.
right. So a tuple is, by definition, not, right. So it has particular slots, and then each of those can have a particular type. But if I define some tuple type, I must define the type of each slot, right?
That's right.
So just throwing fmap at something that, unless you've given it instructions about what to do with the various types in the various slots, it won't know what to do, right?
Right, and that's exactly the point. You've essentially fixed it. You fixed the type. And
Right.
so if the function application does not return the same type, you're screwed, and you have no idea of knowing whether or not you're
Yeah,
returning
yeah. You're
the
asking
same
too
type.
much of it, right?
Yeah,
So, I mean, the whole point of a tuple is to get around the homogeneity, right?
yes,
And hopefully, it's a well structured, it's a well structured thing that has different types and different slots. But what I need to do as a programmer is say, okay, given a tuple of this type, right? Because we're not just going to run up against some strangely raw tuple, right? A tuple must be of some type, and that means that, okay, there's a defined way, there's a defined structure. The first slot will be an integer, the second will be a string, the third will be, I don't know, a geo coordinate or something like that, right? And then I what does it mean to run fmap against that? Fmap has no idea, right? It's like, oh, Jesus Christ, here's a geo coordinate, I don't know what to do here. So I as a programmer need to say, when you're going to run some function on this tuple, you must know that the third one is a geo, right? And then run that. So
right,
it's almost like tuples are really cool. They're like they're points in a multi-dimensional space, right?
right,
So it's like 1 plus 17i, or okay, fine, but that means I need to deal with the real number plane, the real number line, and also the imaginary dimension. And then if we go on from there, we can do quaternions and octonions and all that stuff. But basically, a tuple is the definition of a point in a space that is the number of dimensions. It has the number of dimensions of that tuple's length, right? So just throwing fmap against a tuple, I mean, we talked about this, for an hour or so, but it almost, it's kind of unfair to fmap to expect it to be able to deal with your multi-dimensional value, right?
right.
So
And that's kind of that's really what the driving, and if there's a message that you get away with tonight is there's two things that fmap does for you, but one of them is not dealing with figuring out every sort of complicated case for a functorial structure. There are certain fixed rules that you have to um, just accept when you are writing your functor instances. And one of them is if you are dealing with a higher order kind, all right, a higher kinded type, um, you're going one of those fields or a bunch of those fields may end up getting fixed if you're trying to fmap or provide a functor instance for that type. Um, and that's because the type checker you're asking way too much of it to actually do what it should do to make sure everything is properly type correct. It's impossible to do for that multi-dimensional type. Um, Type checkers, they are only dealing in at most one dimension. All right, they don't really go beyond that. Um, they all, especially when it comes to uh, type construction during the compilation process. Okay, so the one thing to recognize again at the end of all this is really that functors, uh, the rules of functors are identity, compositionality, structure preservation. Functors only apply to the outermost structure in a particular especially fmap only applies to the outermost structure in that's being passed in has with an argument, provided that a valid type class instance is available for that particular outermost structure type. And if you have a complicated nested structure, you're going to have to compose multiple fmaps in order to unwrap that structure in order to properly map over it. These are important things to just recognize and take home today. The final thing that I just wanted to kind of briefly talk about tonight, just because this was a very important discussion that we need to have, is just really dealing with how do we validate our functor instances. Okay, and we've talked about quick check before. Recall quick check just takes allows you to take in kind of a specification and then pass in a function to based on that specification, or run a bunch of different tests against it. And the easiest thing to do for these kinds of when it comes to functor instances is essentially create quick check properties for these instances and then deal with them, and just just call quick check on them so that you can actually validate that it's true. So let's go ahead and do that for our two laws that we want to make sure that we deal with. One is functor identity, which going to take a functor f, right? Take in a type of that's going to be equal. You want to make sure that whatever you return um, from the functor that you're applying, it's going to be a type that has equality defined, and you're going to go ahead and just return f of a function that takes in a functor of a and returns a bool. All right, and what this is doing is just nothing more than it's going to take identity, and then we're just going to validate that if we call the identity on f, it's going to just give us f. All right, that's our function for identity. And then we're going to do the same thing for composition. So we have functor composition. We have two functors. Value has to be f of c, and you have a functor f. And we're going to go ahead and return a function that takes in two arguments, and a function that takes an a to b, and then a function that takes in a b and returns a c. And then we're going to go ahead and create that functor that will go ahead and take an f and a and return a bool, right? And what this is doing is our functor composition function is just going to take in two functions and an argument, and we're just going to make sure the rule of composition matches, which we talked about before. Remember, it's just fmap of f period g is fmap of f composed of fmap of g. And we're going to do the same thing here. We're just going to go fmap x equals nothing more than fmap of g dot f of x. Okay. So now let's go ahead and load this into our REPL. And let's define a quick function here that takes in a list of integers, and then we're just going to go ahead and return a bool on them. And let's do now this is a kind of a reference that's in the uh, the example in the book that we're just covering here. This is just going to take in an x and just call functor identity on it. All right, that's all it's going to do. Did I miss something here? Oh, my apologies. I have to do indentation. Oh, do this. Equals functor identity x. Then indentation is very important there. So we now have a function f. If we do f of 5, we could see that we're going to end up getting an error there because we're not passing in a list. If we pass in 1, 2, you'll see that it's true, and so forth. If you pass in the empty list, it's false. If you do f maybe, maybe 1, you're going to get a complaint about a type being incorrect. But this is if you're hand checking. If you could also just call quick check, which reminds me I have to actually load in quick check. What was the command again? Check. It is import. I think import test. 1 second here. I am having a brain fart today on quick check. Check. Okay, import test.quick check. Oh, it's because I'm not in the prelude anymore. 1 second. Import test.quick check. Is that not? This and that I'm getting at here. Ah, yes, that's right. Because I don't think my stack YAML is. Let me just go and double check my YAML file. Did I actually load quick check into here? Hold on. Okay, I'm going to have to quickly do this. I have to go and update my Cabal file basically to allow me to load quick check here. Got to set this up as I expected. Thought I had it in this particular Cabal file, but I forgot. Give me a second. Go ahead and create a Cabal file here. Yeah. Go ahead and make test.cabal. Let me see if I can do this quickly. Test aim test version. Okay. license file. Okay, so let's just go ahead and go through this. It's going to be. I have to go back and look at my notes because I forgot how to do this. It's been a while since I looked at the Cabal file, so my apologies. Right. Okay. So worry about that. Author test. Okay. Maintainer. I don't think we really need a lot of this. Org. Go ahead and category. Next. Build type. Simple. Version. 10. Fine. Library. Be where we actually expose our modules. And we do a dish, let's call it Functor Overview and GHC options, wall, and tabs for tabs, and then we can actually get started on what's important, which is depends on the base is going to be greater than 4.7. This is all stuff that we talked about before, by the way, for folks who are watching, wondering what this is all about. H spec is not needed. We're using quick check. And we need to specify the source directories and our default language. And I think we're good. Right. All I need. Okay. You need to also hopefully this do touch license and stack build. Let's see if this let us actually move our stack YAML file for this for the time being, and create a new one. Stack YAML.old, and just do a stack init here again. Okay, and let's do a stack build. See what happens. This should all check. We're good. It's downloading it. Okay. All right. Let me go ahead and load up our things. Okay. So, what was I trying to do earlier? Let's define again what we were doing is dealing with the functor identity, which was here. Functor identity x. Okay. So in order for us to do this, we need to first load test.quickcheck. We now have quick check available. And as I showed you earlier, you could simply make sure that if you call 1, 2 on this is all good. To call empty on this, it's all good. If you try to call, a maybe 5 or something like this, it's plain because you're getting a wrong type. But what you could better do is just call quick check on F, and it will go ahead and generate it accordingly. You could also create a simple function, like say functor compose +1 times 2. Oh, sorry, not functor compose, functor composition of +1 times 2. And now if you go in and call, say, uh, x, for example, being, let's say, something that takes in x as an integer, okay, which if we look at the type signature of this, it's just taking a list of integers and returning a bool. We can also call quick check on this, and since it's calling functor composition, it's going to go ahead and double check the fmap stuff that we looked at earlier, what we did before earlier here. It'll generate all those tests, and you can actually provide some arguments to quick check for things related to, say, verbosity. We've gone through some stuff on quick check, so I don't think I have to really uh, reiterate what we've already discussed. I encourage you to go back and look at our stuff on quick check and using HSpec with quick check, just so that you can actually you know what would be the best way to write out your test suites for your each individual things. The point of this is that you don't, although the type checker does not provide you this ability to make sure that you write proper functor instances, with the appropriate test harness available, you can actually write these properties out and just use quick check to handle the checks for you in the off chance you want additional validation. So that's all I had for today, just merely because the fact that this lifting conversation was, I think, a very important one that we need to kind of have. We will finish up our Functor chapter next week, where we go through possibilities, some higher order examples, the IO functor. We're going to talk about some other interesting functors that are available at your functor definition type class instances that are available for you as part of the prelude. And we'll also look at some other things related to just properties of functors that we may want to write up as additional checks inside of our arsenal. So until next time, I'm going to just end it here. If there are any questions, feel free to ask us. Okay, so is that Elixir? Guillermo Rojas. No, this is Haskell. It's not Elixir. I don't know why. We are covering Haskell. Could you be more specific as to what is?
Hey, how often you guys meet actually?
We meet weekly.
Sorry,
We meet weekly.
weekly? Okay.
Yeah, we do. We're covering this, and we meet weekly to talk about Haskell. I'm
Oh,
covering this book, and we are planning on starting to highlight some libraries that I started looking into for Haskell. The purpose is to kind of like kind of show people some of the stuff in Haskell, kind of build up an arsenal on not only learning the language, but also uh, if you want to write Haskell development, professional Haskell development, I feel like while there are books out there, it's easier to go through a tutorial, especially like a YouTube video, and pause it and then, allow people to work through the examples, see how to build actual real software systems in it, and get a sense of what the language is all about. So, Atlanta Functional
Yes.
Programming does not just Haskell; it also does Common Lisp and other languages. We are language agnostic. We want to promote functional programming as a paradigm that people should use as part of building large scale systems, especially nowadays. I feel like with all languages having first class functions, it's you know it's now no excuse. You have to have a really good reason why an API that should be really written to deal with function composition is written in a manner that is not.
Yeah. Functional programming definitely becoming so popular because of big data and other stuff. So the main focus why I'm starting learning Haskell is like I want to be my big data code to be more of functional. So Scala is both the functional and object oriented. So there is no restriction enforced actually when we write code. So I'm basically trying to get that feel actually. So if there is any uh, logic I have to build, so I want to be more of functional way instead of object oriented. So is there any way that I how can I?
So here's the thing: functional and object oriented aren't, they're not. I hope you understand they're not. They're complementary. They're not, exclusive. It's not mutually exclusive. You don't have to just be functional or just be object oriented. I feel like, especially with a language like Scala, there are places where you'd like to be object oriented. Like especially when you're dealing with a lot of state, it might be better to just deal with the object composition pieces. But where you're dealing with like data transformation, building data pipelines, transformation pipelines, and big data are huge, right? Writing those out in a functional manner would at least be more maintainable from my standpoint.
Yeah, I agree. So the thing is like okay, if there is any loop, like I want to write while loop, so instead of while, I can use fold operator, right? So that's what I do actually. So
Right, right,
similarly, like if I have big logic that I can split into functions and then call one by one, maybe I can use higher order functions or such sort actually.
right, right. That's correct.
Yeah, yeah, yeah. So I
So
think yeah.
no, no, that's fine. I want to announce to folks who are listening on our stream and to folks that are around here that you know ha- because this is a good segue. Before I let you all go, just a reminder: Atlanta Functional Programming is looking for speakers to to do talks on whatever language they're using. We are again a language agnostic organization that is trying to deal with and talk about how to build large scale functionally inspired architectures that use principles of higher order functions and the lambda calculus, and in Haskell's case, even uh, types that preserve certain properties using type classes. And If you are interested in giving a talk on something that you're working on, or a language that you think people should really like look at, by all means, ping me or Judd. We'll be more than happy to schedule you as part of our talk series. Um, as usual, many of you know, our staple events are weekly events for Haskell and Common Lisp. If you are looking for a new study group or a new language that you're interested in, kind of, chairing to as part of AFP to promote, by all means, talk to us as well, and we can put you on the schedule for a regular um, meeting, as because we would like to have a lot of these kinds of conversations for these different languages, both in isolation and together in some cases. And I look forward to hearing from you all. I'm available on functionalprogramming.slack as Bugram. I'm also available on the Lisp Discord server for those of you who are on there as well, using the same handle. You can reach me either in either of those places. For folks who are in the Atlanta area, I'm also available on Tech 404. So until next time, I do appreciate all of you for joining us, and I will see you later.